This video is going to cover sections 12.3 and 12.4. So let's start off with rotations. Now we've already talked about this, but I'm going to teach you a few new things. So let's review that when we talk about rotation, if we're talking about the center, and in this case I'm just going to say the center is P. And if I am rotating, let's say point A, which is down here, and I'm going to rotate it up here, and it's going to become A prime. These lines actually don't exist. Remember, you guys have measured those before. These lines, what do you know about them? They have to be congruent. This is called the center of rotation. And remember, sometimes we're going to rotate about the origin, which means 0, 0 is your center of rotation. And sometimes you'll rotate about a point, in which that would be your center of rotation. This angle in here is the angle of rotation. Now, on page 840, this chart is in your book. Now, this is only multiples of 90. If you go by 90 about the origin, now notice here we have a point, xy, that would be your pre-image. This is your image, so we're going counterclockwise. Every time you go 90 degrees counterclockwise, xy is going to map onto negative yx, which means you flip the signs, or you flip the coordinates around, and you take the opposite of your y value. So once again, flip the coordinates around, you take the opposite of the y anytime you go 90 degrees counterclockwise. If you go 180 degrees, now this way it could go either way, 180 degrees, if you start with xy, it's going to become negative x, negative y. So the values just take the opposite of them. That's 180 degrees. So these are shortcuts. Example 1. Find the vertices after you rotate triangle ABC with vertices A, B, and C as shown by 90 degrees about the origin. Now, absolutely, if you want to graph these and then rotate it 90 degrees about the origin, which means we go counterclockwise, you can do that. But you can use your trick or your shortcut where if you take xy, it's going to become negative yx. You take the opposite of y and you flip them. So, A is 2, 1, B is 4, 1, and C is 3, 3. If we map A prime is going to become 1, and that should be negative 1. So 2, negative 1 would become A prime, and that becomes 1, 2. We flipped them, and then took the opposite of your y value. So the opposite of negative 1 is 1, and so it becomes 1, 2. B prime, you can take the opposite of y, so that becomes negative 1, and then flip them. So that becomes negative 1, 4. Take the opposite of y, that's negative 3, flip them. So C prime becomes negative 3, 3. Now, if you really wanted to, let's flip them 90 degrees again. I'm going to show you something. So A double prime, B double prime, C double prime. Let's flip them. 90 degrees counterclockwise one more time. So 1, 2. Take the opposite of 2. That's negative 2, and you flip them. This becomes negative 4, negative 1. And this one would become negative 3, negative 3. So, if we went again, this was 90 degrees counterclockwise. This was 90 degrees counterclockwise. So from A, B, C to A double prime, B double prime, C double prime, we would have gone 180 degrees. And if you remember, 180 degrees is where you have xy. It just becomes the opposite of x and the opposite of y. And look at what we have. 2, negative 1, we take the opposite of both of those, we get negative 2, 1. 4, 1 becomes negative 4, negative 1. 3, 3 becomes negative 3, negative 3. That right there is how you do the opposite. That would be a 180-degree rotation. The next section we're going to talk about is the composition of transformations. So we're in section 12.4. A composition of transformations is one transformation followed by another. Basically, it's more than one transformation in one thing at one time. A glide reflection is a composition of a translation and a reflection across a line parallel to the translation vector. So let me show you how that works. Now, this is found in your book on page 848. Now, you may write this down if you want, or you may just make a mark of yourself, page 848. If you also want to make a Google Doc that you may take screenshots and you put them in your own notes, that's fine as well. So a glide reflection. So it kind of shows you what a glide reflection is. We start with triangle JKL. We first translate the pre-image along a vector. So basically, what we do is we slide it, and notice that the vector here, basically we slid it in a certain direction. So if we slid it to the right, we then have to reflect it over a line that's parallel to the way we slid it. You can't slide something like to the right and then translate it back the other way. You can't do that. You're going to translate it over parallel to the way you've slid it. So if you slide it up, then you'd reflect it over like a vertical line. Here we slide it to the right, we reflect it over a horizontal line. The reflection then is the image across the line. The image after each transformation is congruent. Very important you understand that. This is a rigid motion. A rigid motion is when after you translate something, it's still congruent. By the transitive property of congruence, the final image is congruent to the pre-image, which is going to lead into our next theorem. Theorem 12.4.1 says a composition of two isometries is an isometry. And if you remember, an isometry is a transformation that does not change the shape or size of a figure. So when you reflect something or do multiple things. So if you do more than one isometry, for example, you reflect again, you translate something, you rotate something. All of those things are isometries because they're still congruent shapes. The entire thing is also an isometry. In example 1, in section 12.4, triangle RST has the following vertices. Rotate the triangle 90 degrees about the origin counterclockwise, and then reflect it across the y-axis. So let's first graph our 3 points. I'm going to use, let's use purple. So R is 1, 2, S is 1, 4, and T is negative 3, 4. I connect them to make a triangle. We now need to rotate them counterclockwise 90 degrees. So if I rotate it 90 degrees, I'm going to use my little trick. So R prime, I take the opposite of the y and then flip them. So that'd be negative 2, 1. So negative 2, 1 is R prime. S prime is going to be negative 4, 1. And T prime is going to be negative 4, negative 3. Now I'm going to reflect it across the y-axis. So the y-axis becomes my line of reflection. And if I reflect it over the y-axis, remember if I reflect it over the y-axis, the x values change. So R double prime becomes 2, 1. S double prime becomes 4, 1. And T double prime becomes 4, negative 3. So that would give me 2, 1, 4, 1, and 4, negative 3. So that becomes R double prime, S double prime, and T double prime. So my final order pairs would be 2, 1, 4, 1, and 4, negative 3. Our next theorem is 12, 4, 2. This one says that a composition of two reflections across two parallel lines is equivalent to a translation. So let's just take a look at this. I have two parallel lines. If my blue triangle is reflected across the first line, and then my green triangle is reflected across another line, which gives me the red triangle, these two lines are parallel. That means from blue to red would just be a translation. So the translation vector is perpendicular to the lines. So the translation vector is perpendicular to the parallel lines. The length of the translation vector is twice the distance between the lines. A composition of two reflections across two intersecting lines is equivalent to a rotation. So now let's say I reflect twice, but instead of parallel lines, I just have intersecting lines. So if you look at this one, the blue to the green is just a reflection, and then a green to the red is also a reflection. Well, from blue to red, that's going to be a rotation. Now the center of rotation is the intersection of the lines. So this dot right here where the lines intersect, that's your center of rotation. The angle of rotation is twice the measure of the angle formed by the lines. So if you actually measured this angle, let's say it was 30 degrees, then your angle of rotation would be 60. Example 2. Tabitha is creating a design for an art project. She reflects a figure across line L and then reflects the image across line M. Describe a single transformation that moves the figure from its starting point to its original position. So let's look at our theorem we just talked about. In this problem, we have two intersecting lines. It says in our theorem that the composition of two reflections across two intersecting lines is the equivalent to a rotation. So let's say we start with this one right here. This is her shape. She first reflects it across line L, so we get this one. Then we reflect it across line M. That means that this shape can be rotated to this shape in one single transformation. So we know it's a rotation. How many degrees did she rotate to go from here to here? Well, if you actually move it, let's see if I can do this here. I can rotate it from one shape to the other, and it's a rotation of how many degrees? Here's the great news. If you don't want to measure it, this is what I love. Let's see if I can, let me find a color here. So let's use purple. We're going from here to the shape here. What is the angle right here? What is this angle? Remember, the angle, remember the second part of it. The angle of rotation is twice the measure of the angle formed by the lines. What angle is formed by the lines? It's 90 degrees. We just take twice that. So the rotation is going to be 180 degrees. Now we don't have to say counterclockwise or clockwise because we're going to get the same thing. So the rotation is 180 degrees. Our next theorem, 12.4.3, any translation or rotation is equivalent to a composition of two reflections. So any translation or rotation is equivalent to a composition of two reflections. So let's look at this example. That's on page 850. It says, copy each figure and draw two lines of reflection that produce equivalent transformations. So if we just look at these first two shapes, triangle ABC gives us the image triangle A prime, B prime, C prime. So we know that since this is a translation, we know from up here, a translation is the same thing as two reflections. So this is where it gets a little tricky. We have to go back to our original theorem that we learned. And if you remember our original theorem, it says the length of the translation is twice the distance between the lines. So if we look what we did here, we draw A to A prime. Now you could do B to B prime, C to C prime. A to A prime. We then locate the midpoint, which obviously we can say M. Then we can draw perpendicular bisectors of AM and MA, or MA prime, and we draw our lines of reflection. So this is your line of reflection, this is your other line of reflection, and we're done. So in review, connect any two of the reflection points, so A to A prime, B to B prime, or C to C prime, doesn't matter. Find the midpoint, and then bisect them with lines of reflection.